wabarakatuh. Good afternoon, everyone. Thank you very much for preparing yourself to join this international virtual course, IVC 2022. My name is Muhammad Ridwan. I am a doctoral student in Mathematics Institute Teknologi Bandung. I am very pleased to see you here, and welcome to the fourth day of IVC 2022. It's my pleasure to be the moderator for our speaker today. Please allow me to provide you some information regarding today's lecture. There are two options for the participant of asking question. The first one, you may ask question during the course using the chat box in the Zoom feature. And second option is you could ask directly to the speaker during the question and answer session, and we will have a Q&A session for about 15 minutes before we end today's, and then lecture will be given 2 hours 45 minutes, but speaker is allowed to take some break time in the middle of the course. And let me introduce our speaker today and share my screen. Okay, today's lecture is about introduction to generating functionology. This lecture will be presented by Dr. Hilda Assiyatun. She is associate professor from Institute Teknologi Bandung, Indonesia, and her area of expertise are random graphs, graph Ramsey numbers, graph labelings, metric dimension, partition dimension, and locating chromatic numbers. She is a part of Combinatorial Mathematics Research Group, Faculty of Mathematics and Natural Science. She had been serving, had been serving the department as the head of undergraduate study program in mathematics. And aside of being a lecturer, she is also actively conducting research related to random graphs, graph labelings, and metric dimension. Since November 2020, she is trusted to be the Vice President of Indonesian Mathematics Society, Indo-MS. Moreover, she also serves as a president of Indonesian Combinatorial Society, INACOMS, since May 2022. She received bachelor and master degree in mathematics from Institut Teknologi Bandung, Indonesia, and her Ph.D. in mathematics from University of Melbourne, Australia, in 2001. And this is some selected publications. Her joint with Nabila and Editri Baskoro. This article published in Electronic Journal of Theory and Applications in 2022 in this year. And the second one, joint work with Dian Kartika Sofyan and Editri Baskoro. This article published in Theoretical Computer Science in 2020. And the last one, joint work with Budi Rahajeng and Editri Baskoro, published in Electronic Journal of Graph Theory and Applications in 2019. And for more information and communication, please contact email hilda@math.itb.ac.id. That is short CV of Bu Hilda Assiyatun. Now, our speaker today, Dr. Hilda Assiyatun. Time is yours.
Okay, thank you, Pak Ridwan. Okay, hello everyone. Good afternoon. Assalamualaikum warahmatullahi wabarakatuh. Welcome to our class with topic of Introduction to Generating Functionology. Okay, it is my pleasure to meet you all. Okay, how many of you are there? 81 altogether. Okay. Oh yeah, the moderator has set some rules about this course. Yeah, but I'd like to ask you that if you don't hesitate to ask, so just interrupt me if you need to clarify things. Yeah, no need to wait until the Q&A session. Yeah. Okay. All right. Okay. Okay. First, I would like to know how many of you have heard or have learned generating functions? Should be a lot, yeah. Students coming from ITB should learn a little bit about generating function, yeah, in discrete mathematics course. Okay, okay. So, all right, okay. Hang on, how many of you raise your hand? Just like, oh, all right. Izaz Jamil. Okay, right. And maybe some of you already, yeah, yeah. I'm sure. Those of you who have learned about discrete mathematics have learned a little bit about generating function. Yeah. So today we will learn a bit more, okay, about this topic. It's a very interesting topic. Okay, now let me share my slide with you. Hang on. Where is it? Oh, hang on. Oh, this one. Okay. Okay. I think all of you have, can see my slide now. Yeah. Okay. Hang on. I want to. It's kind of a bit annoying. Yeah. the notification. All right. Okay. The organizer will take care of the student who comes late. Yeah. All right. Okay. Okay. So our topic for this afternoon is introduction to generating functionology. Yeah, there's some what is it? Some small chapter we will discuss this afternoon. Okay, let me see. I need to clear up my screen. Okay. Oh, why it's not working? Okay. Okay, we start with the introduction. Yeah. Okay. In discrete mathematics, there are many problems whose answers is in the form of sequences. Yeah. The generating function will give us tools to obtain the sequence. Yeah. What we mean by obtaining a sequence. Yeah. So we really hope that we can have an explicit and simple, nice formula for our sequence. Yeah. For example, if we have this sequence, yeah, explicit formula of an is n to the 3 plus 3. So we are would say confidently that we already get the answer. Yeah, nice answer. Yeah. However, in many cases, this doesn't happen. Yeah. In many cases, our sequences are so complicated that simple explicit formulas cannot be obtained. Yeah. this is just one example. If we look at the prime number sequence, yeah, we cannot expect to have a simple explicit formula. Yeah. Okay. But even in this condition, yeah, when the sequence are so complex or complicated, we still hope that this method generating function can allow us to learn more, to exploit more about our sequence. Yeah. So the generating function methods offers not only how to get the explicit formula, but also to get other informations about our sequence. Yeah. Okay. Yes. So these are in general what the generating function method can do. Yeah. On the sequence. Yeah. On the sequence. Yeah. The first one, of course, we can use generating function to find an exact formula for our sequence. Yeah. But this is again, it's not always happen. And if you get and even if we get the answer, the explicit formula, maybe not always in a pleasant way, yeah? Not always in a simple way. Yeah. Okay. That's the first one. The second one we can do with generating function is to find a recurrence formula. Yeah. Okay. Most of the time when we work with generating functions, the problem arises from recurrence formula. Yeah. The generating function enable us to find a new recurrence formula that will give us new insight, new understanding about our sequence. Yeah. Okay. And the third one is with generating functions, we can also have we can also find the statistical properties of our sequence. Yeah, maybe if we looking at a sequence and we are interested to find out out about the average, maybe the variance, okay, yeah, about the sequence. Okay, generating function can help. Yeah. And the first one is maybe the most important thing about the things that we can do with generating function is to find asymptotic formulas for the sequence. Yeah. So if we look at a very complicated sequence, yeah. So instead of asking or looking for the exact formula, maybe it's better if we have approximate the formula that can be executed easily. Yeah. So instead of looking for exact formula. Okay. What else? What that we can do with? Oops. I think it's two. Okay. Okay. This one. Yeah. So the other things that we can do with generating function is to prove unimodality or convexity. Yeah. So this is a typical property of combinatorial sequences. Yeah. It has a unimodal property and convex. Yeah. So actually, there are many methods how to prove that a sequence is unimodal. Yeah. Not only generating function, but if generating function can help, yeah, generating function often give the simplest way, yeah, to prove it. Okay. Okay, and then the next one is to prove identities. Yeah, this is also interest one of big interest when we learn about combinatorics. Yeah. Okay, how to prove identities. Yeah. Okay, so for example, here we have identities. Yeah, for a well-known formula. Yeah, this is the binomial coefficients. Yeah, we have these identities. Okay, generating function can help us to prove these identities. Yeah. Okay, jadi how to prove identities using generating function? We will show that the generating function of the left-hand side is the same as the generating function coming from the right hand side. Yeah. Okay, and yeah, so we have this is six things that we can do with generating function. Actually, there's more. Yeah. So for instance, say we are looking at a sequence, and we cannot get the explicit formula, but we get the generating functions, and we find out that this generating function is very similar to other sequence which we already know a bit more. Yeah. So by this, we know that our original problem can be explored more by exploring the other problem that we are already more familiar with. Yeah. Okay. So yeah, these are things we can do with generating functions. Yeah. I haven't said explicitly what is generating function. Yeah. Okay. Oh, okay. This one. Yeah. I think it's a very important quotation from Wilf. Yeah. So what is generating function? Yeah. We can describe generating function in a casual way. Yeah. Like this. A generating function is a clothesline on which we hang up a sequence of numbers for display. Okay. Yeah. So it's look like a clothesline and with colorful t-shirts here. Okay. Oh, hang on. Okay. Okay. Let's see. Oh, why? Okay. So yeah, this is the definition of generating function. Yeah. The ordinary generating function. Yeah. I put ordinary here because actually there are many types of generating function. Okay. Yeah. The ordinary generating function AX of a sequence AN is a power series, yeah, whose coefficient is the sequence. Yeah. So what we mean by this is AX equal to this power series with the coefficient is our sequence. Yeah. So the definition is quite simple. Yeah. The definition of generating function is quite simple. So what is the generating function method? Is a method to obtain the generating function from a sequence. Yeah. Okay. So I already mentioned, but seven things that we can do with generating function, but due to our restricted time, maybe we can only learn or discuss maybe 2 or 3 things, yeah, that we can do with this. Yeah. All right. So I will now give you an example. Okay. Oh, okay. Before the example, I think we need to learn how this method works. Yeah. Okay. Before we try it on a problem. Yeah. All right. So to employ this method, first we are given a recurrence formula for a sequence AN. Okay. So there are a few steps need to be done. Okay, the first one, we have to make sure that the set of values of the free variables of the sequence, say n, yeah, is clearly delineated. Yeah, is clearly well defined. Yeah, okay. And then the second one, we will define our generating function for the sequence. Yeah, so we define AX as the generating function. Yeah, as per definition before. Okay. Okay. So given the recurrence formula, we will multiply both sides by x to the n. Okay. Multiply both sides by x to the n and sum over all values of n for which the recurrence satisfies. Yeah. Holds. Okay. After multiplies both sides by x to the n, okay, we will try to extract yeah, in step 4 and 5, we will try to extract the generating function AX. Yeah. So you see the step is not too complicated. Yeah. And and it works consistently, yeah, regardless how complex or how simple the sequence is. Yeah. All right. Okay. And the last one, actually, the generating function method stops until the step 5. Yeah. But if you want to have more information about the sequence, if you want to know the explicit formula, we can work more. Yeah, we can explore more about the generating function by trying expand the generating function into power series. Yeah, using some methods. Yeah, usually the methods used in this step is how to transform the generating function into rational functions. Yeah. Okay. Okay. Let's see. Okay. I think now we are ready for the first example. But before that, I would like to remind you of these old friends, geometric series. Yeah, we know this is the geometric series with the ratio r, and this geometric series has the sum of this form, yeah, a to a over 1 minus r, if the absolute value of r is less than 1. Yeah, so this is the geometric series. We will use this quite a lot, yeah, in our course today. Okay. Yeah. Okay, we will start with one variable sequences. Yeah. Okay. Okay, this the first example. We have a sequence AN satisfies the recurrence formula. This one, yeah, AN plus 1 equals to AN plus 1. This is valid for n at least 0 with A0 is 0. Yeah. Okay, we will find the sequence using the generating function. Yeah. Okay, if we write down a few members of the sequence, yeah, we will have this. Yeah. If n equals 0, then A0 is 0. If n equals 1, then A1 is 1. Yeah. For n equals 2, A2 is 3, and so on. Okay. Okay. Just looking at this few members, yeah, the first few members of the sequence, we may have a good shot, yeah, to conjecture that the formula in general would be this one, yeah, an equals to 2 to the n minus 1, yeah, for n at least 0, yeah. Yeah, I think, yeah, you can check this is correct, yeah, of course, and you can prove formally using induction, yeah, induction based on this formula, yeah. Okay, all right. So everybody is familiar with induction, yeah? Yeah, can you prove it using induction? Yeah, can you? Okay. Oh, yes. All right. Okay. Now we will use our method, generating function method, to get this explicit formula. Yeah. Okay. So, oh, hang on. Oh, I was wrong. hang on. I clicked the wrong button. Okay, one variable. So this one. Oh, no, wrong again. Hang on, this is the next chapter. Oh, hang on, this. Okay, this already, and then the next one. Oh, why is it? Hang on. Hang on. Maybe I just use this. Okay, this one. Yeah. Okay, again, yeah, this is our recurrence formula. Okay. Okay, so the first step, yeah, remember the first step saying that we must make sure that the the independent variables is well defined. Yeah, I think this is correct. Okay, so the step 1 is clearly fulfilled. Okay, and the step 1, we define a function ax, yeah, for our generating function. So ax equals this power series, yeah, with the coefficient our sequence. Okay, all right. Okay, and then the next step, we will multiply both sides by x to the n. Yeah, we will multiply both sides by x to the n, and then sum over the value of n where the recurrence holds. Yeah. Okay, so we multiply both sides with x to the n, and then sum over n greater or equal 0. Yeah. Okay, now let's see the left hand side first. Yeah. Okay, okay, a(n plus 1 x to the n. Okay, if we expand the sum, okay, we have this few the first few terms. Yeah, a1 ax, a2x, a3 x squared, and so on. Okay, now we will try to take out this ax, yeah, from this expression. Okay, so to get ax, we need to add an extra the first terms, yeah, the constant term a0. Okay, we add this. Okay, and we must multiply all with x. Okay, all right, so this one, okay, yeah, okay, this one is, hang on, oh yeah, this is ax, right? Okay, so we must adjust this by subtracting with a0, yeah, to get, so this one should be equal, okay, and divided by x. Yeah, okay, hang on, I want to oh no. Okay, sorry, I think I need to change this into this mode because I don't know how to do can anybody tell me how to do these things within the full screen mode? Okay, yeah, all right, so the left hand side is equals to ax over x. Yeah, okay, how about the right hand side? Yeah, the right hand side is easier. Okay, the first term equals to 2ax. Yeah, and the second one is our old friend. Yeah, geometric series. Okay, so the sum of x to the n, yeah, and greater or equal 0. Yeah, this series is our geometric series with sum 1 over 1 minus x. Yeah, okay, so now yeah, by combining the left hand side and the right hand side, we will have ax. Yeah, so ax is this rational function. Yeah, okay, so that's the end of the method. Yeah, so the odd numbers an, okay, is the coefficient of, oh, this is wrong, not x, it's supposed to be x to the n. Yeah, the an is the coefficient of x to the n, okay, x to the n in the series expansion of ax. Yeah, so that's why Will says that the generating function is a clothesline to hang up our sequence. Yeah, all right, so we already have the generating function. Now how to get the explicit formula? Yeah, so to get that, we expand ax in a power series. Okay, I think this is quite elemental. Yeah, if you have learned basic calculus, I think you should be able to do it. Yeah, all right, okay, yeah, so everybody can do this fractional fraction. Okay, I need to, you can rational, yeah, all right, rational fraction, yes, Is that Jamil? Yes. Yeah. Okay. So yeah, this is again our old friend geometric series. Yeah. So we know from here that the expansion is this. Yeah, and this is the also the geometric series. Okay. Okay. From here, then we get that the general formula for the coefficient an is 2 to the n minus 1. Yeah, for n equals or for n greater or equals 0. Yeah. So yeah, we again we again have the same answer that we can obtain by using other methods like induction. Yeah. Maybe some of you already wondering why we have to do this. Yeah. When we clearly can do it faster and easier just by using induction. Yeah. Okay. Yeah. Maybe it looks like this is too heavy machinery. Yeah, to handle for small for simple things. Yeah, to handle simple problems. Yeah, it's like killing what is it? Killing a mouse with a big bomb, or maybe. Yeah. Okay. I hope that you will get the answer after more examples. Yeah, why we need to employ this method. Yeah. All right. Yeah. So for this question, for this example, the methods works nicely. Yeah. Okay. Everything is quite elementary. Yeah. All right. Okay. Now we have another one. Yeah. Another example here. Okay. So this is slightly harder. Okay. So again, we have a sequence AN with this recurrence formula. Okay. Okay, and we will use the method to get the explicit formula. Yeah. So if we try to write down the first few members of the sequence, yeah, we will have this 1, 2, 5, 12, 27, 58, 121. Okay. So if we compare with the previous example, I think you may agree that for this sequence, it's not that easy to guess or to conjecture the general formula. Yeah. Okay. It's not, maybe, yeah, we need more time. Yeah. If we just look at this to find the pattern. Yeah. All right. Okay. Now just do the method. Right. Okay. Yeah. I think step 1 also clearly fulfilled. Yeah. We know that this is correct. Yeah. For n equals, or for n greater or equals 0. Okay. Again, the step 2. Okay. Again, we define the generating functions. Okay. Okay. For step 3 and 4, we multiply both sides by x to the n, and then sum over the domain of this recurrence. Yeah. Okay. Okay. Again, we look at the left hand side first. Okay. This is quite similar, I think, as the previous example. Okay. Here we have that the A0 is not 0, right? So we still have one extra terms here. Yeah, -1. Okay. So this is the left hand side, and the right hand side. All right, the right hand side, the first term is easy. Yeah, the first term is easy. It's just 2 times AX. Yeah. Now, okay, how about the second terms? Yeah. Okay, let's look at the second term. Okay, so we have here n x to the n. Yeah, so this is the first few terms, right? So okay, if we take out x, yeah, from all the terms, yeah, we will have, what is it? If we take out x and we have 1, 2x plus 3x squared, and so on, yeah. And we must, yeah, you already observe that this actually is the derivative of x to the n, yeah. Okay, so yeah, this term, yeah, or this series is the derivative of series x to the n, right? And we know that this is our geometric series, yeah, with the sum, this function. All right, so the next, the second term of the right-hand side is this one, okay? Again, by combining the left-hand side and the right-hand side, we obtain, oops, why it's A2? Okay, it's supposed to be just A. Okay. Yeah. We have the generating function. Yeah. Okay, so again, now we can say that our sequence an is the coefficient of x to the n. Again, because maybe I just copied the wrong lines again. Okay, yeah. An is the coefficient of x to the n of the series expansion of ax. Yeah. All right. Okay, now to extract or to get the explicit formula, okay, again we will employ the same technique. Yeah? Okay, can you verify that this is correct? Okay. Or maybe not verified. Maybe can you have this yeah, to verify it's easier. Yeah, just check out that this right hand side equals to the left hand side. Can you get this? Yes. All right. Okay. 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 Now, okay. Oh, hang on. Oh yeah, that's right. Hang on. Okay, yeah. So this is the generating function. So from here we can extract the coefficient by expanding into a series. Yeah. Okay. Okay. This one is the what is it? Geometric series. Yeah. Okay. And this one, this is one we have made before. Yeah. This is the derivative of our geometric series. Again. Yeah. Okay. Okay, from here, yeah, you look at here that we need to clean up a bit, yeah, to make sure that the indices of both sides are the same, yeah. All right. So from here we have that the coefficient of x to the n is this one, yeah, 2 to n plus 1. Okay, from here, okay, n minus 1. Minus n minus 1. Okay, and this is valid for n greater or equal to 0. Okay. Yeah. Okay, you may have noticed that within these two examples that the method works consistently, just like that. Yeah. Regardless the complexity of the recurrence formula, the methods work in the same way. So that's one of the what is it? The advantage of using this method, yeah, because the method works regardless the complexity of the sequence, yeah, work in the same fashion. Okay. All right. Okay.
Excuse me,
Yes.
Bu Hilda.
Yeah.
Looks like there is a question from
Oh,
Ijaz.
sorry. Oh yeah. All right. Yeah. Okay. It just so the partial fraction works nicely. Just can you answer me directly? Can you use your microphone?
Well, I didn't verify it yet.
All right, but you know that you can do it, right?
Yes.
Yes. Okay, good. So your question is what the difference between formal power series and generating function? All right. So if we look at a sequence as a formal power series, we need to be careful about the set of the convergence of the series. Yeah, you know that from the analysis that every power series has the convergence set. Yeah, the sets of All right, but if we look at as a generating function, we might ignore it because we use the series just as an algebraic object to hang up our sequence. So we don't really worry about the convergence, about the sequence. Yeah. Okay.
Okay,
So
thank you.
generating function, it's kind of like more algebraic than analysis. So we can do we can manipulate the sequence, okay, without worrying about the convergences. Yeah, just use the sequence. Sorry, the generating function or the series to hang up our sequence. Yeah, but of course, maybe some use this two notions kind of like in the same interchangeably, but yeah, what we that's my understanding about this. Yeah, so for generating functionologists, they are not worrying about this convergence issue. Okay.
Okay, thank you.
Okay. All right. Okay. Now before we move to more complicated sequence, okay, we need to have some more notation. Okay, so here if fx is a power series of x, then the symbol of this with the brackets, square brackets, x to the n fx means the coefficient of x to the n in the series of fx. Yeah. Okay, so for example here, if we have this, x to the n ex, meaning that we're looking at the coefficient of x to the n in power series of ex. Yeah, so you remember, ex is, what is it? Sum of x to the n. Okay, so yeah, the coefficient of x to the n is 1 over n factorial. Okay, so that the meaning of this symbol. Okay, consequently, if we look at the x to the n of x to the a of x, okay, this would be equal to x to dn minus a fx. Yeah. Okay, and here if we look at the coefficient of beta x to dn fx, that will be equal to 1 over beta, the coefficient of x to the n of fx. Yeah. Okay. Okay. There's more examples here. Okay. Yeah, looking at the same series here. If we look at, we are asking for the coefficient of x to the n over n factorial of ex. Yeah, the answer is 1. Yeah. Okay. Okay. This is our old friends geometric series. Yeah. All right. After this, everyone can follow me.
There is a comment from Muqaddas
Yeah.
Fatima.
Okay. Okay. Thank you. You're not getting. Oh, which one? Which? Can I just call you Fatima?
Yes, ma'am.
Yes. Which one? Which one?
Definition 3, I'm
Can-
not getting it.
Sorry, I can't hear you. Yeah, could you please repeat your?
I'm not getting.
Which one? This one?
Example.
Maybe she is referring to the previous definition.
The previous definition? Oh, not this one. Previous definition. Which one? Fatima, can you just write down, because I can't hear you clearly. Because I think that the definition I just give you is about the notation of the with the square brackets. This is the last definition I give you. All right. Okay, for example, say if I have this, say, what is x to 6 of x? What is it? So this would be the coefficient of x to 5. Agree? Or maybe to make it a bit clear, I just put, say, this is 2x. Yeah. Right. Is it right? Okay. Okay. And what is it? What is the coefficient of x to the 5 of this? What is it? 2? I'm waiting for answers from you. What is it? What is the coefficient of x to the 5 of 1 over 1 minus 2x? Okay, this is 2. Okta answered the question. Is it all right? Yeah. Okay. All right. Yes. Okay. Okay. So Fatima, is it clear now?
Yes, ma'am.
Yes. All right. Okay. Now, hang on. Let me see. I think I will change this. Oh, hang on. Okay, maybe we look at an exercise first. Okay. Yeah. Okay, let's see. Okay, so we will find the ordinary generating function. Yeah, the exponent generating function for the later on. Okay, for this sequence. Yeah. Okay, so what is it? So yeah, the generating function is by definition is this series. Yeah, an x to the n. Okay, so if an equals to okay, what is it? Right. Yes, and this is the derivative of is it correct?
Yes.
Yeah, okay, and this one is what is it? Is our
1/.
Yeah. Okay, yes, that's correct. So what is it? The derivative of this is x 1
Square.
right. Yeah. Okay. Okay. Uh, I will leave the second one for you to read by yourself. Okay, let's see the equation here. What is it? An equals to 8 7 to the n minus 5. Is it 4 to the n? Sorry. Oops. This is from supposed to be not without beta. Yeah. Okay. So what is it? Say it's again we just use the symbol ax for the generating function. Hang on. Okay. Ax by definition is the series of okay. Okay, so this with sum of 8, say minus 5 x to the n by the linearity of the power series, then this should be okay. This is okay. This should equal to minus 5. Oh, sorry, I forgot. Okay, maybe just do it. Minus 5. All right. What is it? Again, this is the geometric series. Yeah. Is 1 over, right? Is it correct? Yes, okay. Okay. Oh, hang on. Minus 5. Okay. Yeah. Yeah, surely you can have a more simplest. Try to have a simpler form. Well, what is it? I don't know. 8 minus, maybe if you want 5. Is it right?
Yes, ma'am.
Yeah, all right. So what is it? 3 plus, oh, hang on. This is quite nice. 3, 1. Is it?
Yes, ma'am.
All right. Yeah. Yeah. All right. Can I have just a short break? I'm thirsty. Maybe 3 minutes break, right?
Okay, ma'am.
All right. Okay, I'm back. Okay, now let's continue with the third example. Hang on. This one. Save first. Okay. Okay, now let's see the next example. This one is 3 terms recurrence. Yeah. So now we look at our old friend as well. Yeah. Fibonacci sequence. Okay. With this recurrence formula. Okay. Okay. Again, yeah, we will employ the same method, generating function. Okay. Okay. So yeah, the first step, I think it's clear. Yeah. So again, we define the generating function for our function, for our sequence, yeah, fx. Okay. Okay. And then again, we multiply both sides by x to the n, and then sum over the value of n. Yeah. In the recurrence formula. Yeah. Okay. So if we look at the left hand side, yeah, we have this, yeah, f2x, okay, okay, starting with n equals 1, yeah, okay, f2x plus f3x squared plus f4x cubed and so on, okay, and this would be equal to this one, right? Okay, so we miss here in the left hand side, we miss the first 2 terms, yeah, f0 and f1, okay, but f0 is 0, right? So yeah, this one is actually the generating function subtracted by the first 2 terms, yeah, okay, okay, divided by x, right? So hope that you now see this a bit routine here, how to do the manipulation, okay. And then the second, the right hand side, okay, the first term equals to fx. Oh no, the first term is equal to fx minus the first term, right? But the first term equals 0. Yeah, so the first term here equals to fx. Yeah. And the second terms, okay, this one, the second terms, this is, yeah, this is fx multiplied by x, yeah. Okay. Okay, so combining the left hand side and the right hand side, we obtain fx equals to this, what is it, rational function, yeah. Okay, again, we will use, okay, so up to this, we have finished the method, yeah. So the method of generating function actually finish when we obtain the generating function, yeah. So now we will do the extra work to get the explicit formula for this Fibonacci sequence. Okay. Okay, again, yeah, with fractional fraction. Yeah. Okay. All right. So we, okay, this is yeah, the what is it? The root of the quadratic polynomial, yeah, below is not are not integers, but of course we can solve it. Yeah. Okay, it's written to have the roots of the quadratic polynomials. Yeah, right. Okay. Again, here we write down the expansion in the form of the geometric series. Yeah. In order to easily extract the coefficient. Yeah. Okay, so this is our generating function. Yeah, in the form of fractional fraction. Okay, so from here we have the explicit formula for our sequence. Yeah, fn equals to 1 over square root of 5. Okay, but now we will look at more closely to this formula. Yeah, so if we look at this first term, yeah, r plus equals to 1 plus the square root of 5 over divided by 2, and the value would be greater than 1. Yeah, while the second one, r minus, yeah, is 1 minus the square root of 5 divided by 2. That would be somewhere around maybe 0.2 minus 0.2. Yeah, so less than, so the magnitude of r minus is less than half. Yeah, I think. Yeah, r minus, which is, what is it, 1 minus this, maybe it's around minus. Yeah, so less than half, right? So if we take n quite big and goes to infinity, yeah, the second term will vanish. Yeah, because yeah, the magnitude is less than half, right? Okay, so from here we can approximate our sequence event as this one. Yeah, just use the first term here, right? Okay. Okay. If you look at this, yeah, I have the table of this. Yeah, this is the approximation of the Fibonacci numbers, but actually this is a very good approximation. Yeah, because if you look at the right hand side, yeah, so if we round it to the nearest integer of the right hand side, we will get the exact value of our sequence. Yeah. Okay. I have write down a few terms here, right? So yeah, if we look at the right hand side of the approximation, right? So this is the right hand side. So if we round it to the nearest integer, then we will obtain the exact value of fn. Yeah. So here, if we have to choose whether we will use the exact formula for this sequence, or we will use the approximate formula, which one will you choose? The first one or the second one? The exact value or the approximate formula? Which one would we choose? Yeah, right. Yeah, because this is much simpler. Yeah, this is much simpler, but we will obtain a very good approximation. Yeah, the same as the exact value. Yeah, rounded to the same exact value. Right. Okay. Yeah, this is because this term, yeah, actually very small. Yeah, this term as n goes to infinity, this term is very small. Right. Okay. All right. Yeah. So these are examples of one variable sequence. Yeah. You see, the first one is very simple one. We can get the explicit formula without this machinery. Yeah, the second one slightly harder, but still easy if you have learned how to get the explicit formula for recurrence using the the characteristic equation. You will get the same answer. Yeah. And then this one is the sequence with 3 terms. Yeah. Okay. Again, in this case, we can also use the characteristic equation to solve it. Yeah. Okay. But as you can see in these 3 examples, that the methods works in the same fashion. Yeah. Okay. Okay. Now we will handle the much harder one, right? Okay. Before this, okay, another reminder of our old friends, the Taylor series. Yeah. Okay. Yeah. So if we have f a function that have with derivatives of all orders, yeah. Okay. Then we can express f as a Taylor series. Okay. Yeah, where the nth terms is the nth derivative of f, yeah, evaluated at a divided by n factorial, okay, times x minus a to the n. Yeah. Okay. Okay. So in particular, if a equals 0, then we have Maclaurin series. Yeah. Okay. Okay. Now let's see the 2 variable sequences. Yeah. Okay. For the first example here, we will rediscover the binomial coefficients. Yeah, I'm sure you have learned about this, yeah, in discrete mathematics, yeah, because that's a very maybe one of the most important, yeah, sequences in combinatorics. Yeah, the binomial coefficients. Okay, now let's pretend that we don't know about this sequence. Okay, and we will employ this method to get this sequence. Yeah. Okay, any question? Oh, yes, yes, thank you, Fatima. Is it the same? Oh, there are 2 Fatima, different. I don't know how to pronounce. Sorry, I'm not sure how to pronounce your name. Mukdas and Nur. Mukdas Fatima and Nur Fatima. All right, okay. All right, yeah. Okay, now, okay, let n and k be integers satisfying this. Okay. The question is, how many ways can we choose a subset of k objects from the set of n objects? Yeah. Okay. So suppose that the answer for this question is this sequence. Yeah. So now our sequence depends on 2 variables n and k. Yeah. Okay. As in previous examples, we know that to employ the method, we need to have a recurrence formula. Yeah. Here we don't have the recurrence formula yet. Yeah. We will construct it. Yeah. We will construct the recurrence formula for our sequence. Yeah. Okay. How to do it? Okay. So here, imagine that we collect all the possible subsets of k objects. Yeah. Okay. We collect all. Okay. And then we divide these subsets into 2 types or into 2 piles. Yeah. In the first pile, we will put all the subset containing n, yeah, containing the largest object containing n. Yeah, in the second pile, we put all subset without n, right? Okay. Okay, so now we will count this subset, yeah, by distinguishing whether they belong to the first pile or the second one. Yeah. Okay. So the first one contains n. The second one do not have n. Yeah. Okay. If you look at the first pile, it's obviously contain f n-1 k-1 subsets. Is it right? Is it correct that in the first pile we will have this many subsets? Yeah, the first pile is those subset with n. Yeah, how many are there? This many. Yeah, so if you erase n from each subset, yeah, we will end up with a subset of size k-1 from n-1 object. Yeah. All right. Okay. Okay, agree. Yeah. Okay. How about the second one now? How many subsets are there in the second pile? Yeah. If we do not have n in this subset, yeah, this would be this pile will contain f n-1 k subsets. Is it right? In the second pile? Yeah. So we distinguish the subset according to whether it contains n or not. Yeah. Okay. Yeah. Okay. Then from here we have this recurrence. Yeah. So f and k equals to, yeah, this one coming from the first pile, f n-1 k plus f n-1 k-1. Right. And this is valid for k at least 0. Yeah. With f and 0 equals 1. Is it right? This assumption that f and 0 equals 1. So this is the number of subset of size 0 from the set of size n. Yeah. So saying that this is the number of empty set, yeah, empty subsets. Yeah. Yeah. Right. Yeah. Okay. Yeah. Okay, now we will do the same procedure again. Yeah, the same fashion. Yeah. All right, we define the, okay, now we define the generating function, okay, only with one variable x, okay, corresponding to this, hang on, the second index, yeah. Okay, so we define a and x, yeah, so it depends on the first variable n x, yeah, equals to this series, yeah. Okay, what's next? Okay, okay, we will multiply both sides by x to the n, yeah, yeah, all right, x to the k, right, yeah, and sum over this range of k. Yeah. Okay, now let's see. Left hand side, I think it's clear that it should be A and X. Agree?
Yes, I agree.
Yeah, all right. How about the right-hand side, the first term in the right-hand side? Is it right? That the first term is an minus 1x? If it's,
Yes.
yeah, multiply by x to the k and then sum over k at least 0, right? And the second terms, right, is x a n minus 1x. Yeah. We have extra factor x here. Yeah. Agree?
Yes, I agree.
Okay. Yeah. Okay, so from here we have that, yeah, an x equals 1 plus x an minus 1x. Yeah. Okay, and this starts from n equals 1 with a0 is 1. Is it right? A0? What is A0 by definition? A0 is F 0 K x to K, right? Yeah. Is that right? Yeah. All right. Yeah. And here, the only non trivial.
Let me call a
Pak
number.
Ridwan,
Hello, Emily.
Pak Ridwan, could you?
Good morning, ma. Well done. Yes.
Hello, Emily.
Okay.
That's the beauty
Mommy, good
of
morning, ma. How my
online
people?
class. Yeah.
Yes, our child is not even ready.
All right.
Okay. Thank you, ma.
Emily.
Could you just mute
Where is it?
her or him, Pak Ridwan?
Yes.
Abi? What do you?
Okay.
All right. Okay.
Can continue.
Yeah. Okay. Yeah. So if you look at this coefficient, yeah, most of them are 0. Yeah, except what is it? F 0 0, which is 1. Correct? Yeah. That's why. Okay. So this actually is, yeah, this would be just, okay. The other one, all other terms would be 0. Yeah. Okay. So that's why we have A0 is 1. Okay. Now, from this relation, yeah, iteratively we can get a and x. Yeah. This would be equals 1 plus x to the n. Okay. Yeah. Valid for n at least 0. Okay. Okay, so this is the generating function of our sequence. Yeah. Okay, now how to, so again, yeah, for the method of the generating function, it terminates here. Yeah, it's finished here. Yeah, once we get the generating function, then we are done. Yeah. Now how to get the what is it? The explicit formula for this sequence. Yeah. In the previous one, we always use the fractional fraction. What is it? How? what is it? Oh, so, how come I forgot the hang on. All right. All right. Okay. I just forget the notion for this. Sorry. Hang on. Okay, now to have this or to get this sequence, we will incorporate Taylor theorems. Yeah. Okay. So what is it? F and K. Yeah. By definition of the generating function, F and K is the coefficient of x to the k. Yeah. Of a and x. Yeah. So F and K is coefficient of x to the k of this, okay, and this would be equal to the derivative, the decay derivative of this function evaluated at x equals 0, okay, divided by k factorial. Yeah. Okay, so what is the k derivatives? Yeah, the first derivative, we move this power to the side again and reduce the power by 1, right? Like this, yeah. And the second derivative, we do the same thing. Yeah, remove the power, the current power to the side and then reduce the power by 1. Yeah. So here we have n and minus 1 and minus 2. Okay, up to n minus this is not m, but this should be k. Sorry. So okay, this is m, it should be k. Okay, I changed my mind in the middle of this, and previously I used m, then I changed my mind. I changed it to k. No, did it very well. Okay, this should be k. All right, so n and minus 1 up to n minus k plus 1. Okay, right, and then evaluate it at x equals 0. Okay, we'll have this, right, and this equals to this one. Yeah, so we rediscover our binomial coefficients, yeah, using this method. Okay. Okay. Hang on. What is it? O 0 when? What is case 1? I don't understand, Nur Fatima. Okay. All right. Now we will make some extension. Yeah. So before that, we restrict our variables for non-negative integers. Now we will extend the variables into all pairs of integers. Yeah. Okay. We observe here that our sequence f and k equals 1 if n at least 0 and k equals 0. Okay. So meaning that we are talking about empty subset. Yeah. Okay. Okay. In particular, f00 is 1. Yeah. Right. So the number of empty subset of an empty subset is 1. Okay. Right. And f and k would be equal 0 if k greater than n, or n less than 0, or m. Oh, it's not m, it's k again. Oh, k less than 0. Is it? All right. It sounds good, this observation. Okay. Okay. How do I call you, Nur or Fatima? Because we have two Fatimas here. All right, yeah. So with this, okay, with this observation, now we can extend our recurrence to all pairs of integers. Okay. Okay, you may check, yeah, that this would be right, yeah. Okay, for example, say, yeah, that not all, yeah, not all, but we just take out one point, yeah, the 0 point, yeah. Okay. Other than that, this recurrence is valid, yeah. Okay, say for example, say n equals 1 and k equals 0, yeah. So the left hand side would say what is the value of the left hand side for this case. N equals 1, k equals 0. The left hand side would be 1, yeah, right?
0.
Yeah. Okay. How about the first terms on the right hand side? So this would be f0, 0. That would be 1 as well. Okay. But this one and the second term would be f 0 minus 1, which is 0. Yeah. So the equation is right. Yeah. You can check. Yeah. Oh, so this recurrence relation is valid for all integers except 0, 0. Okay. So why we bother to extend this the domain of these variables? Yeah. Why we bother to do this? Okay. By this, yeah, by extended the domain, yeah, we will easily get the generating function. Yeah. Okay, we will try. Yeah. The first one, the first generating function is the function of x. Yeah. Right. Now x here corresponding to the second index. Yeah. Okay. Now we will try another types of generating function. Yeah. Okay. This one. Yeah. So now the generating function corresponds to the first index. Yeah. So we define bky equals to this. Yeah. So here now we don't bother to write n greater or equals 0 because this would be valid for all integers now. Because of this extension, we don't have to worry about the range of n anymore. Okay. Yeah. So it will be more convenient for us. Yeah. By extending, by extending this the domain of the indices. Yeah. We no need to worry about this again. Yeah. All right. So we define this generating function, the second generating function. Okay. Now, well, we will do the same thing again. Yeah. Multiply both sides by what? In this step by y to the n. Okay. For what? For everyone. Yeah. Except 0, 0. Okay. Okay. So we multiply this. Okay. Again. Okay. I think from here, yeah, it's easy to see that the left hand side equals to bky. Okay. Okay. And the right hand side, yeah, multiply by y to the n. Yeah. Okay. So we have extra y. Yeah. From here. So this would be y bky. Yeah. Right. And the second one, the second terms, I mean, this is y to the k. Again, we have what is it? Y to the, sorry, y to the n. Y to the n. Again, we have extra y. Okay. So we have y bk minus 1y. Yeah. Okay. So from here, we get that bky equals to y over y 1 minus y bk minus 1. Yeah. Is it right? Yeah, I think so. Yeah. Right. Okay. Now we will try to we haven't got, this is still in iterative formula. We want to know what is bky. Yeah, we note here that b0y is this one, yeah, by definition. Okay, by definition of bk, yeah. If k equals 0, then yeah, we sum up this fn 0 y to the n. Yeah. Okay. And this is equal to this one. Is it right? Yeah. Is it right? Okay. Mukdas Fatima agree with me, right? Yeah, because we know that this is the number of empty subsets. Yeah. Okay, so it should be 1. Okay. Okay, so yeah, we get again the geometric sequence. Yeah. Okay. So with b0y equals this, okay, then iteratively we will have that bky equals to this. Yeah. Okay. So again, here we succeed to obtain the generating function of our sequence. Yeah. Okay. Different generating function. Yeah. Okay. Now again, to what is it, to extract the explicit value, the explicit formula for f and k. Okay, we will use the Taylor theorem. Yeah. Okay. So what is this? F and k is the coefficient of y to the n of this. Okay, and then we use the earlier definition. Yeah. Coefficient of y to the n of this equals to coefficient y to n minus k of this. Okay, and then to get the coefficient of y n minus k, we will use the Taylor theorems. Okay, taking the n to the n minus k derivatives of this, right? Okay, and evaluate it at y equals 0. Yeah. Okay, I think this is not difficult to see. It's quite easy. Yeah. Hang on. Okay, again, this is wrong. Not this is not m, but it should be k. Yeah. Yeah. This is k. Okay. Oops. Okay, this is k. K. Okay. What else? Okay, this should be k as well. Okay. Yeah. Okay. So again, we obtain the binomial coefficient. Yeah, using different generating function. Yeah. Okay. Jadi from this two generating function, we can conclude that our binomial coefficient, yeah, has two generating function. Yeah, there should be the coefficient of x to the k of this, or coefficient of y to the n of this. Yeah. All right. So based on our experience, what do you think of this question? Is there any other form of generating function for f and k? What do you think? So what is it, Nur Fatima? I don't know. You answer yes for this question or the previous questions. right? So you should try to have this, yeah? So if in the previous two, we have generating function depends only one variable, okay, you should try this. Okay, f and what's it, k, say, maybe, yeah, okay, I just swap it, yeah, just for convenience, okay. Okay, and here we don't have to worry about the range of this because we have extended the what is it, the recurrence formula to all integers, yeah? Okay, you should try this. Okay, let's see, yeah, how we ended up with this, yeah, what kind of generating function we will have. Okay, all right, okay, okay, let me think. Okay, I think I will return to this exercise. All right. Maybe we can try this one first, yeah, before I continue with the next two variables sequence. Yeah. Okay, I will. Let's try number 3. Yeah. Okay. Okay. Yeah. So here we have that fx is equals to this one. Yeah. Oops, this one is wrong as well. It should be 0. Oh. And oops, sorry, x to the n. Yeah. This is the ordinary power series, or yeah, the ordinary generating function. Yeah. So this is what we have. Okay, now we will express the generating function of this sequence. Yeah. So what is this? Yeah. So by definition, okay, we will have, what is it? A0 plus 0x plus A2 x squared plus 0 x to the 3 plus what is it, x4 and so on. Yeah. Yeah, so this would be equal to A0 plus A2x squared A4x to the 4. Okay. So what is this in terms of f? Anyone? What is this? Looks like our original f.
Ma'am, f
Yeah.
and f into 2 and k. Because it's all even A2, A4 and
Yeah, all right, yeah, all the odd terms are gone, missing. Yeah, so what is this?
ma'am, I think F into 2n, if I think 2n, because all are even when n is 0, we get A naught. When n is 1, we get A2 and A4. I
Mhm.
think so.
Any other suggestion? What is this?
F into 2n k. Ma'am, 2n.
I'm not sure I understand your answer, Fatima. Okay, let's see. So, so if fx is this one, yeah, so fx is equals a like this, yeah. Okay, what is f minus x? Yeah, what is f minus x? That should be a0 minus a1x plus a2x square. What is it? The next one? Minus a3x cubed. Is it right? Okay,
Yes,
is it?
right.
Do you agree with this? That f minus x is this one?
Yes.
Right? Okay, so if we add up these two series, what will we get here? Okay, if we adding up this, then all the odd terms will disappear. Okay. Okay, so then back to this. So what is this then? This should be fx. Right? I'm not sure I understand what you mean by the series of f2 and k. Are we talking about the same problem, or are you referring to the previous examples?
Oh, ma'am, she's talking about the same problem.
The same problem? In this problem, we only have one variable, yeah? You in your answer, you have two variables there. I understand that. It should be two variables, right? Yeah. Okay. All right. Yeah, you can try the first and the second one. Yeah, just okay. Look, yeah, by how to express this in terms of maybe f or plus other simple functions. Yeah, we know. Right. Okay. Okay. Again, 3-minute breaks. Yeah. I need to stretch my legs. All right. And have a drink. Okay, I'm back. All right. Okay. Now let's go back to two variable sequences. Okay. Okay. So here we discover binomial coefficients. Okay. Now we will look at another important sequence here in combinatorics. Okay. Okay. A partition of a set. Yeah. Okay. A partition of a set S is a collection of non-empty pairwise disjoint sets whose union is S. Yeah. Okay. The sets into which S is partitioned are called the classes of the partitions. Yeah. Okay. This is an example of this partition of sets. Yeah. So suppose we look at this sets of the first 5 positive integers. Okay. Or 5 natural numbers. Okay. Okay. So, and we want to partition this set. Yeah. Okay. There's many ways to do that. Okay. One of them is as this one. Yeah. Okay. So in this partition, we have 3 classes. Okay. And the first class, consists of 1, 2, 3. The second class consists of 4, and then the third class is the third class consists of 5. Okay. When we talk about this partition, yeah, we do not care about the order of the elements within a class, nor the order of the classes. Yeah. So we don't care about this. Yeah. Okay. So the important things is that we want to know who is together and who is apart. Okay. So this is our interest here when we talk about the partition of a set. Okay. Here we have the list of all partition of the set of for positive integers for first positive integers, yeah, into 2 classes. Yeah. Okay. Here. Okay. I think how many? Okay. 1, 2, 3. Yeah. The first 3 partitions. Each class has 2 members. Okay. Okay. In the second, the types of partition. The first class consists of 3 members, and the second one is a singleton. Yeah. Okay. Okay. So the number of partition of this set into 2 classes, 7. Yeah. Okay. Now we want to look at this sequence. Yeah. Okay. So we want to answer the question is how many partitions of set of n objects into k classes. Okay. Okay. How many of this? Yeah. And we will use this notation, yeah, for this number. And this number is called the Stirling number of the second kind. Yeah, you should find out if you just heard this kind of number. Yeah, you should find out about Stirling number of the first kind. Yeah, what is this? Yeah, so this one is the second one. Yeah. Okay, so with this notation, yeah, we have that. What is it? I don't know how to read out this symbol. Yeah. Just say that the partition 4 to 2 is 7. Yeah. Okay. Yes. Similar to the previous example of binomial coefficients, yeah, we need to construct the recurrence for this sequence, yeah, or for these numbers, yeah. Again, yeah, okay. Imagine that in front of us, we have all the collection of partition, the possible partition of the set of n objects into k classes, yeah. Okay, there are this many of them, yeah. Okay, again, we will divide this collection into two piles, yeah. Okay, how to distinguish between these two piles, yeah. Okay, into the first one, we will collect all those partitions in which n lives in a class by itself, yeah. So it's a singleton, yeah. N lives as a singleton, yeah. This is in the first pile, yeah. And in the second piles, yeah, of course, the remaining, yeah, meaning that in the second piles, n lives with other letters, yeah, with other numbers, okay. Okay, now we will count how many are there in the first piles and how many in the second piles, yeah. Okay. Okay, yeah, the first pile, in the first pile, n living alone, yeah. Okay, so if we erase n in each if we erase n, so meaning we erase one class, yeah, one class of singleton, okay. Okay, we will end up with a collection of all partitions of n-1 objects into k-1, yeah, into k-1 classes, yeah. Okay, because we just erase one class consisting singleton n, yeah. Okay, so how many are there? Yeah, it should be this many, yeah. n-1, k-1. Okay. Okay, so these are the number of partition in the first pile, yeah. Okay, how about the second one, yeah? In the second one, n lives together with other numbers, yeah, or letters, okay. Okay, here again, what we do is we erase n, yeah, whenever it appears, we erase it, gitu ya. So what happened here, because n always lives with other letters, yeah, when we erase n, yeah, the class will be remains, yeah. Okay, okay, because there's other occupants in this class, yeah. Okay, oops, sorry, hang on, sorry, I just, all right. How many are there in this second piles, yeah. Okay, so after we erasing n, erase n for every class, okay. Now the pile contain partition of sorry, with I think, okay, hang on, okay, just ignore the notification. Okay, in the second pile again, yeah, after we erase n for every partition, yeah, we will end up with the partition of n-1 objects into k classes, yeah. But note here that each one of these partition appears not only once but k times, yeah. Why k times? Yeah, because n can appear in any class, okay. We have k class, okay, and n can appear in any class, yeah. So the same partition of n-1 object will appears multiple times, yeah, for to be exact, k times, yeah. Okay, for example, if we look at this okay, say this one, yeah, into two classes, yeah. So now say we erase 4 for every place. Okay, See, here we end up with partition of 3 objects into 2 classes. Yeah, but we see here, yeah, this partition appear twice. Okay. Okay, this partition, okay, appear twice. Okay. What else? Yeah, and this one as well. Oops, sorry. I want to hang on. Uh-oh, why? Okay, I want to change the color. Again, where is it? This one. And which one? One. Okay, this one. Yeah. Is there any? All right. Yeah. So again, we end up with partition of 3 objects into 2 classes. Yeah, where each partition appears 2 times. Yeah, twice. Yeah, in this example. Okay. So in general, this is what we have. Yeah. In the second parts, yeah, we will have the partition of n-1 object into k classes that appear k times. Yeah. So this means that in the second pile there are this many partitions. Okay, so summing up the first pile and the second piles, and we get this recurrence formula for our number. Yeah, Stirling of the second kind. Yeah. Okay. Yeah. So what are the range for n and k? Yeah. Okay. Yeah. So to make the calculation easier, yeah, we would like to have this as wide as possible. So yeah, can we define this to all pairs of integers like the previous one? Okay. Okay. Yeah, if we look at this, okay, yeah, we note here, yeah, that nk equals 0 when n is not 0 but k is 0. Yeah, so if there's no class, of course there is no way to do it. Okay, that will be 0. Yeah, but we set 0 equals 1. Yeah. Okay. Yeah, 0 so the number way to partition an empty set into an empty set. Okay, just one way to do it. Yeah. Okay. And also, yeah, nk equals 0 when k greater than n, or n negative, or again, this is not this is k. Yeah. Okay. So with this, with this convention, we extend the definition of this number into all pairs of integers. Okay. So our recurrence formula will be valid in this. In all pairs of integers except 0, 0. Yeah, because at 0, 0 we will have the value is 1. Yeah. Okay. Again, you should check that this is correct. Yeah. Yeah, the natural domain for this, of course, and yeah, the natural number for this should be n greater than k, greater or equal k. Yeah, this is the natural range. Yeah, but by this convention, we can extend into all pairs of integers. Yeah, and this would make our work easier. Yeah, when we employ the method. Yeah. Okay. So we already have the the recurrence formula, and we will do the same thing again. Yeah. Okay. We will multiply. Oh, okay. We define first. Yeah. We define first. Okay. All right. Yeah. We define what type of generating function we will use. Okay, so yeah, similar to previous example, yeah, there are three natural candidates, yeah, for generating functions. Yeah, okay, the first one's depends only one variables, and second one yeah, depends on two variables. Yeah, okay, yeah, let's see here. Yeah, because of the convention, because we extend the domain of the indexes into all pairs of integers. Yeah, we don't have to worry about this. Yeah, just say n, say k, whatever. Yeah, will be valid. Yeah, okay, all right. Yeah, now let's try the first one. Yeah, okay, let's try the first one. Okay, yeah, again, yeah, now it's quite routine, yeah, to do that. Okay, look at again this, hang on, where is it? Yeah, so we multiply with x to the n. Yeah, x to the n. Okay, x to the n. So the left hand side easy, that should be the generating function ak. Okay, but this one, if we multiply with x to the n, we have extra x. Yeah, okay, here if we multiply with x to the n, also we have extra x. Yeah, okay, so this is what we have. Okay, right, so the index is equals to the second part. Yeah, k minus 1, k. Okay, so so from here I think it's easy to see that akx equals to yeah, this one. Yeah, akx equals to x over 1 minus kx a k minus 1. Yeah, all right. Yeah, I think okay, it's clear. Yeah, okay, this for k starting from 1 and a0 equals 1. Yeah, you should check, should be easy to see that a0, oh, if it's this is 0, means yeah, that the number of class is 0, all vanish except the first one when n also 0. Yeah, yeah, and that the value is equals 1. Yeah, that's why we have a0x equals 1. Okay, all right, so iteratively again here, yeah, we will have akx is this one. Yeah, okay, so this is the generating function for our Stirling number. Yeah, okay, so again, regarding the methods, actually the methods already finished here. Yeah, so the remaining work will be how we extract the what is it, the explicit formula for our sequence. Yeah, our Stirling number. Okay, now how to do this? Yeah, okay, I think we go back to the same method like in the one variable. Yeah, okay, we will transform this, yeah, into partial fraction. Okay, okay, yeah, you see that we have how many k factors, yeah, in the lower part. This, yeah, okay, this, yeah, it should be it can be transformed into this. Yeah, the summation of this. Okay, okay, and okay, hang on. Yeah, I think it's right. Yeah. Oh, I think yes, maybe I changed my mind again. I think here I changed J into R. Yeah, okay, this should be R. Yeah, okay, how to find alphas? Yeah, okay, yeah, this is the trick. Yeah, should be easier. It's a standard trick. Yeah, we multiply both sides by 1 minus Rx, yeah. Okay, so if we multiply both, that's actually it's like cheating actually, yeah. Multiply both sides by 1 minus Rx. Okay, so here if we do that, okay, we the factor of 1 minus Rx will be cancelled. Okay, and then we substitute X to by 1 over R. Okay, from here all the terms in the right hand side would will disappear, yeah, except one terms. Okay, from there we will have that AR equals to this, yeah, 1 over, yeah, X substituted by 1 over R. Okay, bit messy, yeah, already a bit messy here. Okay, but we can make this one a bit nicer, yeah, by tidy it up. Okay, you see here all divided by R. Okay, how many there if we divide it by R, we will have the terms R minus okay, if you look at this divided by R minus 1, R minus 2, R minus 3, so on until 1. Yeah, so we'll have this factor R minus 1 factorial, and then we will have this many minus 1, yeah, from here. Okay, we collect them all in this factor. Okay, and then the R from the below going up, yeah, we will have R to K minus 1. Yeah. Okay, so we can tidy it up a little bit to get alpha R, yeah, in this partial fraction. Okay, so from here, what is our sequence? The Stirling number is the coefficient of x to the n of this equals to coefficient x to the n minus k of this, and this is with partial fraction is equals to this, right? Yeah, it's already looks bigger. Yeah, you should look at this. Okay, this is some kind, yeah, it's so many things going on here. Yeah, okay. Anyway, yeah, by tidy up, yeah, we must be very careful here. We can have the explicit formula for our Stirling, not the nice one, not simple one, yeah, but we get it. Yeah, we get the explicit formula for Stirling, yeah, for the number of partitions of a set of n objects into k classes. Yeah. Okay. Yeah. So the methods succeed. Yeah. The methods give us the explicit formula for our sequence. Yeah. Okay. Okay. Any question or comments after this? Okay. I see. I hope that I have convinced you that this method, the generating function method, works in the same way, in the same fashion. Yeah. Regardless the complexity of the sequence. Yeah. Can be very powerful. Yeah. Okay. Okay. Now go back to the previous one. Okay. This is something interesting. Yeah. Hang on. Yeah. Originally, we define, yeah, naturally this number is defined on n greater or equal k. Yeah. But actually, this formula works for any n and k positive or non-negative integer. Yeah. So supposingly, yeah, because we are already tired and sleepy, and we write down things like this: n equals, say, 7, but k equals 13. Okay, and just put it in this messy summation, yeah, this summation will be clever enough to give the correct answer, which is, what is the correct answer for this? The number of partition of 7 objects into certain classes. So what is the answer? 0, yes. Yeah. Okay, so this messy summation, it's quite clever. Yeah, if we put the wrong, yeah, it's unnatural value of n and k, and this will give us the right answer. Yeah, maybe if you don't trust me, you can try the easiest. Say maybe let's see. Let's try it. Okay, this is messy as well. Okay, let's try say 2, 3. Yeah, just put it in here. So what is this? Okay, so it should be the sum of r equals 1 to 3. Okay, minus 1. Okay, what is it? 3 minus r, r2. Okay, like this, yeah. R factorial, k at 3 minus r factorial. Yeah. Okay, if we plug in into this sum. All right, let's try. What is this? When r equals 1, this should be, what is it? Minus 1 to the 2. 1 to the 2. What is it? 1 factorial, 2 factorial. Yeah, this is the first terms, and the second one, okay, plus minus 1. What is it? R equals 2, so minus 1, 2. Okay, over 2 factorial, 1 factorial. Okay, and the last one is, what is it? Minus 1, 0, 3. Okay, over 3 factorial, 0 factorial. Okay. What is it? What is the sum of these 3 terms? Yeah. Rian, are you answering this question? Rian?
The previous question.
Oh, the previous question. All right. How about this one? Anyone? Yeah, I think it's correct. Yeah. I think this one. Yeah. Right. Yeah. This one is it half? Right. And this minus 2 over here, and this 1.5 minus 1.5 here. Yeah. Okay. So yeah, this is 0. Okay. So this messy explicit formula for Stirling It's quite smart. Yeah. Okay. So that's why it's here. I put so not necessarily n greater than k. Yeah. N and k can be any non-negative integer. Yeah. All right. Okay. Okay. So yeah, we still have a few minutes. Okay. Now the last part. Okay. Okay. So if in Stirling number second kind, yeah, this is the number of ways to partition the set of n elements into k classes, right? Okay. Now suppose we do not care how many classes are there, but we want to know the number of ways to partition this set of n elements. Yeah. We don't really care about the number of the classes. Okay. Okay. And this number is called Bell number. Yeah. Okay. Okay. The convention is to define that B0 equals 1. Yeah. So the number of ways to partition empty set is 1. Yeah. As an empty set. Okay. Okay. So the sequence of Bell numbers, okay, begins like this. Yeah. It's 1 for n equals 0, 1 when n equals 1. I think it's clear. Yeah. 2 when n equals 2. Yeah. Okay, and so on. Okay. Okay. So now the question is, can we find an explicit formula for Bell numbers? Okay. Yeah, the answer is trivial. Yeah. Because we already have the Stirling formula, the messy one. Okay. The Bell number actually is just the sum of the Stirling formula, the Stirling number. Yeah. So if we sum up the Stirling number from k equals 1 to n, then we will have explicit formula for Bn. Yeah, so it's nothing great about this. That's obvious, right? Okay. Okay. And you see that the Stirling number, it's already messy. Yeah. So if we add more summation there, yeah, you can imagine that will be much messier. Yeah. Okay. We will take advantage of this the fact that the formula for a string number is very smart. Yeah, knows when it goes 0. Knows. Yeah, the formula knows. Okay, so taking advantage of that. Yeah. Okay. We will try to sum this Stirling formula to get the Bell numbers. Yeah. Okay, so by definition, this is the Bell number. Yeah, the sum of the Stirling number. Yeah, from k1 up to n. Right. Okay. Because of the formula is so smart, now we can change the upper bound to m, where m is any number greater than n. Okay, because the formula will know. Yeah. Okay. So we change the upper bound of the summation. Okay, and then we plug in the explicit formula for a Stirling number. Yeah, this is the messy one we already obtained before. Okay, from here we do some tidied up. Okay, now we interchange the summation. Yeah, so here we start with k. Okay, then followed by j. Okay, now we change it. Yeah, we start with j followed by k. Yeah. Okay, if you are worried about this, don't be. Okay, because this is actually quite easy. Yeah, you can see it by drawing some diagram. Let's say this the horizontal axis belongs to, say, to what is it? To j, yeah, and the vertical axis belongs to k, right? So what we do here, okay, so we start with k equals 1, okay, and then we start j equals 1, okay, and then okay, we stop here, and then we add the value of k. Okay, now k equals 2, and then j is follow suit 1, 2. This, yeah. Okay, now we add one more to k equals 3, and then j follow suit 1, 2, 3. Yeah, this is how we do the summation in the second line here. Yeah. Okay. Yeah. So this is kind of like we move to this, okay, and then we going like this, okay. Yeah. Okay. You see here that we can change. We can do what is it? What's it? Another counting. Yeah. Okay. No need to do this way. Okay. We can do this way. Yeah. We start here with okay. Actually, this is just for number. Yeah. Okay. This is 1, 2, 3. We only sum all the vertices in this, yeah, in this region. Yeah. Okay. So we can do in different way by starting from here. I use different color. Yeah, the same vertices. Okay, we start with here j equals 1. Okay, going up until m. Okay, after that, sorry, I think I need to use this. Yeah, the same thing. Maybe too fast. Okay. Okay. So in this version, we start with j equals 1, and then the k, start with the same number. Okay, going up until m. Okay, so things like this. Yeah, same. Okay, and then j, add one more value. Okay, 2, and then okay, going up again. Yeah. So basically we do the same counting, yeah, but in different way. Okay, that's why we can change this summation, yeah, into this. Yeah, we interchange the order. Yeah. Okay, why we do this? Okay, because we want to have this nice, oops, hang on, this nice formula. Okay, okay, with by changing this, okay, we will have okay, I think it's too big. Yeah, bn equals to this. Yeah, and this one, oh, okay, okay, this one it's quite intriguing. Yeah? Because this one it's quite familiar. Yeah, yeah, this related to the exponent function. Yeah, more precisely, this very close to e to the -1. Okay, this one, right? So yeah, by doing this, then we will have that. Okay, by keeping n and r fixed, and we let m goes to infinity, then we will have a much simpler formula. Yeah, asymptotic formula for Bell numbers. Yeah, that is Bn equals is 1 over e, the sum of this. Yeah, so if we look at the previous one, yeah, see, okay, so this one, okay, goes to 1 over e. Okay, and this one, yeah, is the series we have here. Yeah. Okay. Yeah. All right. So yeah, beyond the explicit formula will be messy, but now we have kind of like what is it? The asymptotic formula, which look nicer, and more than that, yeah, this form, yeah, will motivate us to define another kind of generating function, yeah, by putting another extra factor, which is factorial and factorial. Yeah. So yeah, so motivating by this form. Yeah. Now we define another form of generating function, which we call the exponential generating function, like this. Yeah. So the difference between this and the previous one is that we have extra factor 1 over n factorial. Yeah. In the previous one, in the ordinary generating function, we don't have that factor. Yeah. Okay. So this is the exponential generating function. Okay. And okay, I think I almost finished. Okay. And again, yeah, if we do the same method to this, yeah, what is it? Multiplying both sides by x to the n over n factorial, and then sum over the domain of n, okay, and try to extract px, yeah, like the previous examples, okay, and we will have that the px, the exponential generating function for PL numbers, yeah, it's the same method, yeah, okay. Again, here we need to tidy it up a little bit, okay, and then remembering our old friend exponential function, yeah, a to the x, okay, we know, yeah, this is an xn, all right, okay. So just remembering this, some basic, and we will end up with this, okay. So Bell numbers are complicated, yeah, the sum of complicated sum, all right, but the exponential generating function is simple. Actually, it's quite beautiful, right? Yeah. Okay, so now we can say that what is the Bell number? The Bell number is the sequence with whose generating function is this. Okay, yeah, in the terms of generating function, we can say that. Yeah. Okay. Okay, I think I have a little
Yes.
bit more. Yes. Oh,
Yes.
it's any question?
No, I think our time is
All
running
right.
out.
All
Yes.
right. Okay. Yeah, I will give you the what is it? The notes, yeah. Okay.
Okay.
Actually, I want to show you that using the last generating function, okay, we can have a new recurrence formula for Bell numbers. Okay, so as I promised in the first in the beginning of this class, yeah, there's so many things that we can do with generating function. So we have seen how we get the explicit formula, we get how we get the asymptotic approximation, and then yeah, this one, a new recurrence coming from generating function. I think, okay, thank you, Pak Ridwan. I think I stop here. Yeah.
Okay. What a nice presentation by Bu Hilda Assiyatun. Thank you very much for your explanation about generating functionology.
Yeah.
Now,
this is just the intro. Just the
yes.
intro. Yeah, a little bit of generating function.
Okay.
Yeah. All right. Okay.
Now let us have a quick Q&A session.
All right.
May 2 or 3 questions may be enough. And
Okay.
I have,
Yes.
I think you could raise your virtual hand to ask our speaker directly. Okay. I think already there are several questions already answered in the chat while discussed while lecture.
Yeah.
And maybe okay, do you have any question? Okay, check chat.
Yeah.
Okay. Okay. Should be slide
right.
and recording video should be in Stipendi.
Yeah, I will revise some. You know that I made few mistakes in my slides. Yeah, I will revise it before I put it in, or before I send it to the committee. But I will keep the my writing when we did the exercise. Yeah, I will keep the writing, but I will revise the slide. Yeah, you should try. Yeah, I have prepared some more questions. You should try. All right. Okay. Thank you so much for having me.
Thank you, Bu Hilda. Maybe we waiting for the participant ask the question. Could could Maya help me to take the picture together?
Okay.
Oh, should I stop
Yeah.
sharing?
Yes. Yes, ma'am.
Yeah. Yes.
Okay. For everyone that want to be in this picture, please turn on your camera first. There is 4 slides in here, so I will take the picture from the first slide. Wait. Okay. Let me take the picture for the first slide. 1, 2, 3. Oh, sorry, bentar. Oh, sorry, wait a minute. 1, 2, 3. Next, we move to the second slide.
Should I keep posting like?
Yeah. 1, 2, 3. The third slide. 1, 2, 3. Okay, for the last one. 1, 2, 3. Okay, it's done. Thank you very much. Pak Ridwan still.
Okay. Any question for this lecture today? Okay, I think it's time to end the lecture today. And thanks one more time. Thanks to Bu Hilda, and thanks to all participants for being active today. I sincerely apologize if I made any mistake in moderating this seminar. I hope you guys learned a lot from today's lecture. And see you tomorrow. Take care and bye-bye.
Okay, bye-bye. Thank you.
Thank you. Thank you, Bu Hilda.
Thank you, Hilda.